This is the colligative properties of solutions. The term colligative property refers to a solution property that depends only upon the concentration of the dissolved solute particles, but does not depend upon the solute's identity. Okay, so that's what a colligative property means. It's a property that depends only on concentration, but does not depend on the identity of the solute. And there are 4 colligative properties that we're going to learn about. The first one is called vapor pressure lowering. So I'll remind you what the vapor pressure of a solution is, and then the vapor pressure of the solution is lower than that of the pure solvent. Everybody knows what a boiling point is. So boiling point elevation, that's the temperature at which the solution boils. It's always larger than the boiling point of the pure solvent. Freezing point depression, conversely, the freezing point of a solution is always lower than the freezing point of the pure solvent. And lastly, a term that you may have learned about already in your biology coursework, the osmotic pressure of a solution is a colligative property. And so I'll talk about that as well. So the vapor pressure lowering. Take a look at this figure down below. Okay, so here we've got pure water, and what I'm going to tell you is that the pure water and the vapor above the pure water, or the vapor above the liquid, are in equilibrium. So if you seal up the water at a fixed temperature, what will happen is the liquid is going to be constantly evaporating, the vapor is going to be constantly condensing. Once the rate of those two equal one another, so once the rate of vaporization equals the rate of condensation, you're going to have an equilibrium established, and then the vapor pressure of the vapor above the liquid, or the pressure of the vapor above the liquid, is called the vapor pressure of the liquid. Okay? So the vapor pressure of a liquid is the partial pressure of a vapor that is in equilibrium with its liquid phase. All liquids have a vapor pressure. And that vapor pressure depends upon temperature. So as you increase the temperature of the liquid, that's going to drive more of the molecules into the vapor phase, and so consequently the vapor pressure is going to increase. And if you keep increasing the temperature, eventually you're going to hit the boiling point of the liquid. That is the temperature at which the vapor pressure of the liquid equals the external pressure. So let's suppose that the liquid is exposed to a total pressure of 1 atmosphere. Once you get the vapor pressure of that liquid substance up to 1 atmosphere, then it's going to start to boil. Let's see here. We've already discussed, we haven't discussed yet Raoult's law. So we've discussed an ideal solution. That's one where the molecules of the solute and the solvent are roughly the same in terms of their size, shape, and chemical structure. Another aspect of the ideal solution is that both components of the solution obey Raoult's law. Raoult's law is given for us right here. It refers to a solution, and what it tells us is that the vapor pressure of a liquid I in a solution is equal to the vapor pressure of the pure liquid I times the mole fraction of component I in the liquid phase. Okay, so the star here denotes the vapor pressure, say, of the pure water. The pressure without the star denotes the vapor pressure of the water in the solution. And what we find is that the vapor pressure of the water in the solution is lower than the vapor pressure of the pure liquid at the same temperature. Raoult's law tells us how to calculate the vapor pressure in solution from the pure component's vapor pressure by using the mole fraction as a multiplicative factor. Then if you go to calculate what is the difference between the vapor pressure in solution minus the vapor pressure of the pure component. So let's suppose that component 1 is our solvent. So this is the vapor pressure of the water in the solution minus the pure water's vapor pressure. You can substitute in, I'll do the math explicitly here. You can substitute in Raoult's law right here, x1 P1 star minus P1 star. You can simplify that. You factor out the P1 star, and it gives you x1 minus 1. Well, due to the fact that x1 plus x2 must add up to 1 for a binary mixture, you can write this as minus x2 P1 star. And so what it tells us is that the amount by which the vapor pressure changes, first, it's always negative. So the vapor pressure always is lowered. That's why we call it the vapor pressure lowering. And the magnitude of the change depends only on the concentration of the solute. It depends on the mole fraction of the solute. It does not depend on what the solute is. Now it depends upon what the solvent is, because the solvent's vapor pressure is determined by the identity of the solvent. But the mole fraction of the solute is independent of the solute. So that's what makes it a colligative property, because the magnitude of the property does not depend upon the identity of the solute, it only depends on its concentration. Oh, here's an interesting technique related to vapor pressures. It's very familiar to people from Kentucky. Distillation. So it's a technique for separating the components of a liquid mixture. So, for example, if you had a mixture of ethanol and water, and you wanted to increase the concentration of the ethanol in the mixture, you could use the distillation technique. For other types of liquids, you can actually use the technique to completely separate the components of the mixtures. That doesn't work for alcohol and water, but for other liquids, for ideal solutions, it would work. And so here's an experimental apparatus where you've got a, this is the sample mixture. This is the distillation still pot. You heat that up. Then you have a condenser here. The vapor phase above this mixture is going to be enriched in the more volatile liquid, and so you can collect the more volatile solution, or the solution that's enriched in the more volatile component. You can collect that over here in the receiving flask. On the industrial scale, fractional distillation is used to, for example, its most important application is to purify components from petroleum. So you have raw crude oil coming in here, and then through a series of I don't even know what you would call them, pipes, basically, that would be best, I guess. What you do is you heat up the crude oil, and then the components with the lower molecular masses, they rise to the top. Okay, because they're the more volatile components, and the heavier components of the crude oil, they stay at the bottom, and then you can separate them at different points in these large containers. And so this is how you, for example, separate the gasolines from the unusable crude oil residue, and get these various petrochemicals out, which can be further purified and then turned into reagents to be used in chemistry, or you can use them, send them off to be used to fuel cars and power the world, all that sort of stuff. So fractional distillation is very important in the modern world. All right, so here we have a simple problem involving Raoult's law and the vapor pressure lowering. So they want us to calculate the vapor pressure lowering of water when 5.68 grams of glucose is dissolved in 25.2 grams of water. they give us the vapor pressure of water is 23.8 millimeters of mercury. And then they want us to calculate the vapor pressure of the solution. So the formula that we have here will allow us to calculate the vapor pressure lowering. But the actual vapor pressure of the solution, so this is the vapor pressure lowering, that's the delta, the change in the vapor pressure. But then the actual vapor pressure will be equal to the vapor pressure of the pure substance plus the delta P. Okay, so there's two things they're asking us to calculate. First, calculate the vapor pressure lowering. That's the delta P. And then they want us to calculate the vapor pressure of the solution. That's going to be the vapor pressure of the solvent plus the change in the vapor pressure. Note that the vapor pressure of the glucose, which is a non-volatile component, is assumed to be 0. So, to get delta P, we need to know the mole fraction. So we're going to take the mass of the glucose divided by the molar mass of the glucose. That's number of moles. We'll do the same thing in the denominator, but we need to add to that the water. Mass of water divided by molar mass of water. So I'm just going to do that on my calculator here real quick. I'm going to take the 5.68. I'm going to divide that by 180.16. So that gives me 0.0315 moles in the numerator divided by quantity, I'm going to do it again, 5.68 divided by 180.16 plus 25.2 grams of water divided by 18.02, quantity closed. So I'm getting a mole fraction for the glucose. Getting a mole fraction is 0.022 unitless. The delta P then is going to be minus the mole fraction, x glucose times the times now the vapor pressure of the water. So minus 0.022 times 23.8 millimeters of mercury. So it decreases a little bit. It decreases by 0.524 millimeters of mercury. Small but measurable. Then to get the vapor pressure of the solution, it's going to be the vapor pressure of the water plus the delta P. And so that's the answer that I'm getting for this one. Here we've got a number of problems. Let me just look at them quickly to see if there's any tricky ones. Compute the vapor pressure of an ideal solution. We've got some glycerin and some ethanol. Vapor pressure of pure ethanol is this. So this is the same problem. They want you to calculate the vapor pressure of the solution. Here we have a urea and water solution. The urea is, you pretend that to be non-volatile. They want you to calculate the vapor pressure of the solution. Here we've got some naphthalene and chloroform. Calculate the vapor pressure lowering. I believe it's the same problem. So all three of these problems are identical to the one that we've just worked. You know, the difference is the amount of the materials that you have and their molar masses. But it's solved using the exact same equations. All right, well, let's move on to our next colligative properties. We've got the boiling point elevation and the freezing point depression. I went ahead and put these on the same slide because they follow the same equations. So, or very similar equations. So the boiling point of a solvent in solution is the boiling point of the pure solvent plus the absolute value of delta T. And delta T is given by KBM. It's always positive, but I just wanted to to make the formula very similar to the freezing point, I wanted to just go ahead and wrap that in absolute value. So this is always a positive quantity that you're adding to the pure solvent's boiling point. Delta T, the boiling point elevation, depends on a constant Kb, which takes on a particular value for a given solvent. And then M is the molality of the solute. So this is the boiling point elevation, and this is the boiling point of the solution. So notice those are different quantities, the boiling point elevation and the boiling point of the solvent. The amount, the magnitude of the boiling point elevation depends only on the solute. Kb, I should say it depends only on the concentration of the solute. It does not depend upon the identity of the solute. Kb is a constant for the solvent, so Kb takes on different values for different solvents. The freezing point depression is similar, except we use a minus sign when we calculate the freezing temperature of the solvent. So it's the pure solvent's freezing temperature minus the freezing point depression, or the freezing point lowering. So delta T, it's a constant Kf times the molality. Kb and Kf are different numbers for different liquids. What are some applications of this sort of stuff? Well, the freezing point lowering is mostly used to de-ice sidewalks. You sprinkle salt, which dissolves on the ice, and it lowers the melting point of the water. And so it can melt sidewalk ice, it can melt roads, it can melt the ice that forms on roadways. Here they're spraying probably ethylene glycol on a plane to keep the components of the wings from freezing when it takes off in cold weather conditions. So using a de-icer to prevent the ice crystals from forming on the mechanical components of the plane. Here is a simple problem for freezing point depression freezing point depression and boiling point elevation. So what are the boiling and freezing points of a 0.33 molal solution in benzene? And then they want to know what's the boiling point elevation and what's the freezing point depression compared to pure benzene. So I'm going to go ahead and write out the formulas again. So we'll start with the boiling point elevation. The boiling point elevation is going to be Kb times the molality, and the new boiling point, I should write that B, is Tb star plus delta Tb. Okay, so this is the elevation and this is the new boiling point. And so we can calculate this. We'll take the 2.53, that's degrees Celsius, kilograms per mole, and we multiply it by the molality, 0.33 moles per kilogram. We see that those cancel out. So that gives us 0.834 degrees Celsius. I guess I should have made it 0.83 degrees Celsius. And now, to get the boiling point, we would take the boiling point of benzene, 80.1 degrees Celsius, and add to that the 0.83 degrees Celsius. And so that's going to give us 80.9 degrees Celsius. So the boiling point elevation is relatively small. Let's compare that with the freezing point depression. So similar formulas. Delta T freezing is Kf times M. Okay, so Kf, you'll notice, is a little bit larger, 5.12. And so the delta Tf is a little bit larger than the delta Tb. So we get a drop of 1.69 degrees Celsius. And so when we go to get the freezing point of the solution, it's Tf star minus delta Tf. For benzene, that's 5.5 degrees Celsius minus 1.69 degrees Celsius. So 3.81. So a larger drop in the boiling point, a larger drop in the freezing point compared to the rise in the rise in the boiling point. And that's true for all compounds. For all compounds, you're going to find that Kf is a larger value than Kb, therefore the freezing point depression is a larger effect than the boiling point elevation. All right, I'm going to go ahead and work this one because it's a different type of problem, and it illustrates another application of freezing point depression. So here we have a solution that contains 4 grams of a non-electrolyte that is dissolved in a known amount of benzene, and it's found to freeze at 2.32 degrees Celsius. And then we're being asked to calculate what is the molar mass of the compound. So we can calculate delta Tf. Delta Tf is going to be the temperature, and I'm going to do this in absolute values, the temperature of the freezing point, it's the freezing point temperature minus the pure freezing temperature. It doesn't matter which way you go, we're going to get a positive number because we've used absolute values. And that, so we can calculate this quantity. And then this is going to be equal to Kf times M, where the molality is the moles of solute. So this would be the moles, I'm just going to put solute, divided by the kilograms of solvent. And we'll go a little bit further. Moles of solute is the mass of solute divided by the molar mass of the solute. And that's what we want. Okay, so delta T. So what we'll do is we'll rearrange this, solving for the molar mass of the solute. It will be Kf times the mass of the solute. That's going to be divided by the kilograms of the solvent divided by delta T. And so we can start plugging these numbers in. So we'll have 5.12 for the mass, for the molality of the solute. It was, no, not molality. This should be, the notation's a little confusing. Mass of the solute. And so that was 4.00 grams. we're going to divide that by the kilograms of the solvent, which is going to be 55.0 times 10 to the minus 3 kilograms. And then the delta T is going to be 5. We'll take 5.5 minus 2.32. And that's degrees Celsius. And I'm getting an estimate of 117 grams per mole. So this is one application of the colligative properties. You can use the freezing point depression to estimate the molar mass of an unknown solute. So here we've got some more problems that I imagine are very similar. Find the boiling point of a solution. What is the boiling point of a solution? What is the freezing point? Here, a molar mass problem. So we've done examples of all of these. These are meant for you to practice. Really the only thing that's changed is the nature, is the identity of the solute and the solvent, which changes the Kb or Kf values as the case may be, and of course the amounts and molar masses will be different as well. So here we have, this is just a conceptual slide. What this slide does is it ties back to something that we learned about phase diagrams in General Chemistry 1. And so recall what a phase diagram does is it provides it indicates under what set of conditions is a given phase stable. So here we're plotting pressure versus temperature. Let's take a look at the solid lines first. Okay, so within this region, so on this side of that region, the solid phase is the most stable. In between these two regions here, the liquid phase is the most stable, and then below this solid line here, the gas phase is the most stable. So if you have a temperature that's this value, whatever this value is, and a pressure, whatever this value is, the gas is the stable phase. If you go to higher pressures, the liquid phase is stable. If you go to low temperatures and high pressures, the solid is favored. Okay, so that's the phase diagram. Now, what happens when you make a solution? Okay, what that does is it essentially takes this part of the graph and it slides it down this curve. So the amount by which the graph drops is the vapor pressure lowering. Right? This curve here, it's called a coexistence curve, and it represents, along this curve, you have both gas and liquid in equilibrium. And so this would be for a pure substance. Now, when you make a solution, what happens is that the vapor pressure of the liquid drops. It's the vapor pressure lowering. Okay? And then what you see is that changes the curves somewhat. And so I forgot to mention, let's take a look at this horizontal line. Okay, this is 1 atmosphere pressure. At 1 atmosphere, this point right here, this represents the boiling point temperature of the pure solvent. Now, when you make a solution and the vapor pressure drops, you see that the intersection between 1 atmosphere and the new coexistence curve occurs at a higher temperature, okay, corresponding to a boiling point elevation. Likewise, this point right here, this represents the freezing temperature, right? It's the point along the solid-liquid coexistence curve. This point represents the freezing temperature at 1 atmosphere. Now, if you make of a pure system, pure solvent, now when you make the solution, what happens is it moves this curve, right? It moves to this dashed line here. And so now you see that the freezing point has decreased relative to the pure solvent's freezing point, corresponding to freezing point depression. Well, let's talk about the last colligative property, osmotic pressure. So osmosis is a diffusion process, and it's easiest to understand by looking at the figure. So we have this this U-shaped tube here, and there's a semi-permeable membrane. Okay, we'll put pure solvent on one side of the membrane, and we'll put a solution on the other side. And the solute in this case is presumed to be a rather large and bulky molecule. So for example, a big protein dissolved in water, or a carbohydrate, or just some type of large molecule that cannot pass through the semi-permeable membrane. However, the solvent can pass through the semi-permeable membrane. Well, the effect of this semi-permeable membrane and the fact that you have a difference in concentration of the solute on this side of the membrane versus that side of the membrane causes the solvent to try to flood the solution in a vain attempt to equalize the concentration of the solute on both sides. Okay. What happens is that causes the level of liquid on this solution side of the apparatus to increase. That creates a pressure, a downward pressure called the osmotic pressure, which is a hydrostatic pressure associated with the mass of this column of liquid pushing down via the force of gravity on the liquid. So eventually, the action of the solvent to move from the left side of the apparatus to the right side of the apparatus is counterbalanced by the osmotic pressure, the hydrostatic pressure associated with this excess of height of the liquid column on the right-hand side of the system. And so once those two things come into balance, this height of the liquid on this side of the diagram above that side is proportional to what we call the osmotic pressure, which can be calculated by taking the concentration of the solution and multiplying by R times T. This symbol here, this is an uppercase symbol for pi. Some applications of osmosis. Reverse osmosis can be used to purify water. I happen to have a reverse osmosis water filter underneath my sink at home. The idea here is that if you take contaminated water or that has some solute in it that you don't want, and you have appropriate membranes, you can push down on the solution side, and that will cause the the water to go through the semi-permeable membrane, leaving the presumably toxic solute behind. In biology, you guys have probably seen this a cartoon like this before. In order to have a healthy cell, you need the concentration of the electrolytes inside the cell to match the concentration of electrolytes outside the cell. We say that the solution is isotonic in that case, and the cells are healthy. However, if you have a hypotonic solution, meaning the solution has, let's see if I can remember how this works. If the solution inside the cell has a lower concentration of electrolytes than you have outside the cell, no, I've got it backwards. If the concentration of electrolytes inside the cell is larger than the concentration of electrolytes outside of the cell, we call the solution hypotonic, which will cause the solvent to flood the cell membrane, causing the cells to puff up and explode eventually through a process called hemolysis. which can actually be desirable because you might want to blow up the cells so you can study what's inside of it. The opposite of that, if you have a hypertonic solution, this is where the concentration of the electrolytes outside the cell are too large compared to the concentration inside the cell. What will happen is that the solvent, the water inside the cell, will leave the cell going into the surrounding fluid, causing the cells to shrivel up and basically die in a process called crenation. Here's some problems dealing with osmosis. What is the osmotic pressure of a 0.3 molar solution of glucose in water that is to be used for intravenous infusion at body temperature? So we'll take pi equals CRT. The molarity is 0.30 moles per liter. We'll take that times the gas constant, 0.0826 liters atmospheres mole Kelvin. Take that times the 21. Take that times the temperature. We need to convert the 37 to Kelvin, 310, times 0.0821 times 0.3, and you get an osmotic pressure of 7.6 ATMs. Let me double check that. 37 plus 273, 310 times 0.0821 times 0.3. Yep, I get the same number again. So that's the temperature, or that's the osmotic pressure in atmospheres that we get for that number. For the second one, this is a molar mass one. These are kind of fun. So it's the same deal. We've got the osmotic pressure. The molarity is equal to the number of moles of the solute divided by the volume of the solution. And the number of moles is equal to the mass of the solute times divided by the molar mass of the solute. So we can rearrange this. The molar mass is going to be equal to the mass times RT divided by the osmotic pressure times the volume of solution. And so putting in these numbers here, we've got 10 grams, 10.0 grams of hemoglobin, 0.0821 liter atmospheres, moles Kelvin, 22 degrees Celsius, getting 295 Kelvin. Divide that by the osmotic pressure. Oh, I need to convert the 5.9 torrs to atmospheres. So 5.9 torrs, that'll be 1 atmosphere is 760 torrs. I'm getting 7.76 times 10 to the minus 3 atmospheres. So put that in, 7.76. And then the volume of solution, 0.500 liters. Running these numbers through the calculator. I'm getting an estimate of 62.4 times 10 to the 3 grams per mole, which for a protein like hemoglobin is not an unusual number. We are typically working with small molecules in general chemistry where the molar masses are small, but in biochemistry the molar masses are quite large, and so that's not unusual. So this is our estimate based on the osmotic pressure of a hemoglobin solution, what the molar mass is, and that's one of the neat applications of in chemistry, at least, of osmotic pressure. Is it like the other colligative properties, it can be used to estimate molar masses. You're going to find that these problems are identical, so I'll leave them to you as exercises. One last but very important topic, the colligative properties of electrolytes. And so the thing that you have to watch out for with electrolytes is that when they dissolve, you get multiple particles forming, right? You get both cations and anions. So if we were to say that, I had a 1 molal solution of sodium chloride, which completely dissociates, that would be like having twice the number of particles dissolved. And that's going to have an impact, a doubling impact, on the colligative properties, which depend on the number of dissolved particles. And so for ionic compounds, we are going to introduce a little fudge factor here called the Van Hoff factor, which is the number of moles of dissolved particles per dissolved moles of formula units. Okay, so for sodium chloride, which has 2 cations for every 1 formula unit that dissolves, the Van Hoff factor would be 2. For a non-electrolyte that does not form ions, the Van Hoff factor would be 1. For a weak electrolyte, a compound that doesn't completely dissociate to form ions, the Van Hoff factor would be between 1 and 2, but it's likely closer to 1. Okay, so those are the rules that we have here at the bottom. And then for each of our colligative properties that we've looked at, you just introduce a little Van Hoff factor in front. And so if you're talking about a strong electrolyte like sodium chloride, you would double the impact on the freezing point depression, or double the impact on the boiling point elevation. This should be the Greek symbol pi. You would double the effect on the osmotic pressure. This slide is meant to illustrate that even for strong electrolytes, the Van Hoff factor would not be quite equal to the number of ions. It'll be slightly less because the ions can pair up in solution, even if only temporarily. Nevertheless, this has an effect on the Van Hoff factor. So what we're to do here is to figure out for problems 1 through 8, we're supposed to estimate the Van Hoff factor for each solute. And given that the molality of each solution is the same, we want to determine which one would have the lowest freezing point, which one would have the smallest freezing point depression, which one would have the lowest boiling point, etc. So for all of these compounds, what we're going to do is try to figure out what the Van Hoff factor is. Now, number 1 is a tricky one. You have to have some knowledge left over from Chem 120, your first semester of chemistry, to know how to do number 1. If you don't have that knowledge, you'd probably say, okay, number 1 is a molecular compound. I don't see why it would form ions in solution, so I would say that the Van Hoff factor would be 1. However, you'd be wrong. Ammonia, NH3, is the quintessential example of a weak base. And so it turns out, and this is one that you should probably just commit to memory, When ammonia is dissolved in water, it will react with the water. A proton will be transferred from the water to give NH4 plus aqueous, leaving behind some hydroxide. So we'd have a weakly basic solution. And notice I said weakly and I used the double-sided arrow, meaning that not 100% of the molecules will dissociate. So what we would expect for the Van Hoff factor is that it would be between 1 and 2. Likely it's going to be closer to 1. So I would just say that it's I is approximately 1, but still greater than 1. What about 2? What would the Van Hoff factor for HCl be? Well, you'll either recognize that as a strong acid or you won't. At a certain point in this class, you're going to need to recognize HCl as a strong acid. HCl will 100% dissociate with water to give hydronium. Here, I said it but didn't write it the correct way. Like so. Leaving behind chloride. As I said, 100% will dissociate. So here we would take I, the Van Hoff factor, to be equal to 2, because there's 2 ions that form for every formula unit that dissociate here. For ammonia, for each one that dissociates, you get 2. However, not all of them dissociate. For number 3, we recognize that as an ionic compound. It's group 1 cation. It's totally soluble. You get these ions. It's one directional. The Van Hoff factor here is going to be 3. 2 cations and 1 anion. For number 4, C6H12O6. This is a sugar type molecule. It dissolves readily in water, but it is a molecular compound and it does not react with water. So the Van Hoff factor here is just 1. For 5, this is acetic acid. We've looked at this before already. It is not a bad idea for you to memorize this reaction. Acetic acid is the quintessential example of a weak acid. And so that's its acid ionization reaction. Again, it's a weak acid, so it only partially dissociates in water. So I is going to be greater than 1, less than 2, probably closer to 1. But still, it's going to be greater than 1 because it does ionize to some extent. For 6, we've got iron 3 sulfate, which is going to be very soluble. In water. You're going to have 2 irons and 3 sulfates. So I here is going to be 5. We've got 5 ions dissolved for every formula unit that dissolves. For 7, sodium hydroxide is going to be, I really need to get them all on one page, but I don't have enough space. That's too bad. Well, I'll just write it out. For 7, you're going to form sodium ions and hydroxide ions. So the Van Hoff factor here is going to be 2. It's an ionic compound. 8, that's methanol that we've been working with. Methanol is a molecular compound it does not ionize in water. It's like sugar. I mean, it's an alcohol, but it's like sugar in the sense that it doesn't dissociate to form ions. It's not a hydroxide. So here the Van Hoff factor is 1. Okay, so now that we're able to, or that I've shown you what you need to be able to do, you need to be able to look at a chemical formula and figure out, is this, what's the Van Hoff factor for this compound? So you need to be able to do part A, which is what we've done. Now, given the Van Hoff factors, we need to figure out which solution would have the lowest freezing point. Okay, so let's write that out. The freezing point of the solution. Well, the freezing point is the TF, and that's TF star minus delta TF. That's the freezing point lowering. That's the freezing point. Minus IKFM. Okay, so they want to know which of these solutions is going to have the smallest value of TF. Well, TF star and KF and M are the same for each solution, right? It's assumed that they're all water, so KF is the same, TF star is the same. And then we're told that the molality is the same for each solution, 0.01. Okay? So really, what's going to make a difference is the Van Hoff factor. So what's going to make TF the smallest? The solution that has the largest Van Hoff factor. Looking at the solutions we have, the iron 3 sulfate had the largest Van Hoff factor, therefore it will have the lowest freezing point. So that was part B. For part C, which solution has the lowest freezing point? Depression. And so that's just the delta T. Which one will have the smallest value of delta T? Well, that will be the one with the smallest Van Hoff factor. We've got two winners there. The sugar and the methanol both have a Van Hoff factor of 1, so they both satisfy the answer. It's not a perfect question. Part D. Which would have the lowest boiling point? TB is TB star plus delta TB, which is TB star plus I KBM. TB star, KB, and M are the same for all solutions in this case. Which one would have the smallest value of TB? That would be the one with the smallest value of I. And so, again, the sugar and the methanol would satisfy that. For part E, which would have the highest boiling point elevation? Well, the boiling point elevation is the delta TB. So which one has the largest value of I? Would have the largest value of delta TB. Again, that is the iron 3 sulfate one that had a Van Hoff factor of 5. Which one would have the largest osmotic pressure? You put the Van Hoff factor in front, that's the molarity. Molarity is going to be the same for all of them. Well, maybe not quite, but close enough. Let's assume that the molarity for each solution is 1 mole per liter. Let's make it easy on ourselves. So we'll have to rewrite the problem a little bit. Assuming that all the molarities are the same, which one would have the largest osmotic pressure? The one with the largest value of the Van Hoff factor. So again, that would be the iron 3 sulfate. So it's very important when you get into the test for this part of the material, that you are able to make a distinction between the freezing point and the freezing point depression, make a distinction between the boiling point and the boiling point elevation. If you get those confused, you're going to mess up the problem, right? So that's what I wanted to warn you about. I'm going to go ahead and stop this video right here, and in the next one we'll discuss the colloids.